Here with our conjugate zeros theorem, if we have a polynomial that has, again, only real coefficients, which is pretty much all we're going to be dealing with, and we know that one of our zeros is non-real, a and b are real numbers, then we know that we have to have the conjugate as also a zero. If a plus bi is a zero, then we know that a minus bi also has a zero. If we don't have these conjugate pairs, then we can't have a polynomial with only real coefficients, because the conjugate pairs always multiply to give us real values. And so now we're going to do the same idea, but we're given the condition that we want the least possible degree, it needs only real coefficients, and it has the given zeros. So we're given the zeros 3 and 2 plus I. But in order for us to have only real coefficients, this implies that 2 minus I also has to be a zero. We have to have both. Likewise with b, we have 2 and 3i, but the only way to get only real coefficients is if negative 3i is also a zero. So using our same idea before as x minus k for all of our factors, these are our k values. So we have x minus 3 as one of our factors, and then we have x minus 2 plus I as another factor, and x minus 2 minus I as another factor. So with x minus 3, x minus 2 minus I, and x minus 2 plus I, we end up with our three factors. Now we just need to multiply these all out. There's no other condition about what the function needs to evaluate, so we don't need to include the a value that we have before. So we don't need to solve for any specific a value. So we're just going to assume that we're probably going to have a leading coefficient of 1. Or maybe some other value depending on how it works out. The easiest thing to do when we're multiplying these is you want to multiply the non-real parts first. That way we can multiply out and simplify out the non-real portions of these factors. So we distribute the first term, x squared minus 2x plus xi, negative 2x plus 4 minus 2i, and negative xi plus 2i minus I squared. Well, xi and negative xi are going to cancel. Negative 2i and 2i are going to cancel. And then I squared simplifies to negative 1, which changes us a minus negative 1 to a plus 1. So we have x squared minus 2x plus 4 plus 1, which gives us x squared minus 4x plus 5. So now we've gotten rid of the non-real parts. We just need to do our last distributive, which will finish out our function. We distribute x to the third minus 4x squared plus 5x minus 3x squared plus 12x minus 15, x to the third minus 7x squared plus 12x, or 17x plus 17x minus 15. There's our polynomial of least degree, only real coefficients with the given zeros. We can do the same idea here. Our factors will be x minus 2, x minus 3i, and x plus 3i. When we multiply these, when we actually multiply and we get a sum of cubes instead of a difference of cubes, since we have non-real numbers, giving us x squared plus 9. Again, the I squared is negative 1. Negative 9 times negative 1 is positive 9. And we distribute again. X to the third minus 2x squared plus 9x minus 18. Last but not least, we're going to do what we did in the previous lesson, and we're going to find all the zeros of a function given one of the zeros. We're given that 1 minus I is a 0. But keep in mind that we also know that 1 plus I is a 0. So we're actually given two zeros that we're going to use with synthetic division to find the rest of the zeros. So we start with 1 minus I. And we set up our synthetic. Bring down the 1. Multiply. Add. Now I'm not going to show all the steps for every time, but I want you to keep in mind that when you are multiplying the complex numbers, you're going to have to do distributed property. So we get negative 6, negative I squared, or sorry, negative I. Then we get plus 6I and plus I squared. So these combine to give us 5I. This turns into a negative 1. So we have negative 7 plus 5I. Negative 7 plus 5I. So when you're doing your distributive property, make sure that you're paying really close attention, especially with the I squared and that sign change. And also remember that our remainder has to be 0. So if you get a remainder other than 0, you know you messed something up along the way. So we go ahead and we add these. We get 11 plus 5I. We multiply 11 plus 5I by 1 minus I, and we get 16 minus 6I. We add those, we get negative 6 minus 6I. Multiply those, we get negative 12. And then there's the remainder that we need. Now, we have a cubic polynomial here, but these have non-real coefficients. So we can't really do a whole lot with that, except that we know that 1 plus I is also a 0. So we can go ahead and do synthetic division again with 1 plus I. And we can ignore the column with the remainder in it. We only need to do the first 4 terms, because this is our constant down here at the end. So same idea. Now it's going to clean up really well, and we need to end up with all real coefficients down here in order for us to continue. If you don't get real coefficients, it's not going to work. So we multiply and we get 1 plus I, which adds to give us negative 5. Our i's cancel. We get negative 5 minus 5I. Again, our i's cancel, leaving us with 6. Then we get 6 plus 6I, and then all of those cancel, leaving our remainder of 0. So we have x squared minus 5x plus 6. Now to find our last zeros, we can either factor or use quadratic formula if it's not factorable. This is factorable. And so we can solve and get our zeros. And so all of our zeros are 1 minus I, 1 plus I, 2, and 3. Now sometimes they'll just ask for the rest of the zeros. Here they said find all zeros. Sometimes they'll say find the rest of the zeros. And if that was the case, you would only list those 3. I encourage you to pause and try this one on your own. It'll be a little bit easier because I is going to be purely imaginary, and so the multiplication is going to be a little simpler. And again, as a little hint, negative I is also a 0, and our result is also not factorable, so you will have to use the quadratic formula when you get to your quadratic. But go ahead and pause now and try it on your own, and then I'll write out the work for you to see and compare it. We set up our value of I for our 0 in our synthetic division. Multiply, or bring down, and we multiply. We add. We multiply. We add. We multiply. We add. And we multiply. And we get our remainder of 0. Let me move this 26 over. Keep all of these in line and separate. So we get our remainder of 0, and then we go ahead and we do synthetic again with our conjugate, negative I. And again, we can ignore the column with the remainder. So 1, negative I gives us 10. Negative 10I gives us 26. Negative 26I gives us our remainder of 0. So we're left with x squared plus 10x plus 26. Now, this quadratic is not factorable, so we're going to use our quadratic formula. When we simplify the discriminant, we get negative 4. Now that tells us that we're going to have 2 more non-real solutions, so all 4 of our solutions will be non-real. So we go ahead and simplify, we get 2I over 2, and we simplify our fraction, we get negative 5 plus minus 2I. So then our 4 zeros are I, negative 5 plus 2I, and then negative 5 minus 2I. And those are all 4 of our zeros. And sometimes it's helpful, you can actually compare the graph and look at the intercepts. And for the graph of B specifically, you'll see that your x-axis is way down low, and the function kind of does this thing way up high, and it never crosses the x-axis down here, which is why all of our roots are in complex non-real numbers.